standard grenade. Cycle gives you... Okay, we're going to look at impulse and momentum. We motivate impulse and momentum in a similar way to that with which we motivated the concept of energy. You recall that for the concept of energy we took the equation of motion Vf squared minus V naught squared equals 2AS and substituted acceleration equals F over m, and we got the definition of work and kinetic energy. In this case we're going to do something very similar and actually somewhat simpler. We know that final velocity is initial velocity plus acceleration times delta t. This is because acceleration times delta t is the change in velocity. V naught's the initial velocity, so when we add the two we get Vf. And acceleration equals F over m. We combine these, of course, we can substitute F over m for the acceleration, and we get this equation with F over m in place of the acceleration. If we solve for F delta t, we get the answer to the question, what's the result of applying a force, a known force, for a given time interval? And the result of that is to change mv. So we have F delta t equals mvf minus mv naught. F delta t is called the impulse. mv is what we call momentum, so that the change in mv, which is mvf minus mv naught, is the change in momentum. Now we're assuming here implicitly that the mass is constant. There are cases where mass is not constant, and we'll take a look at those within the context of the calculus here in a few minutes. The units of F delta t are units of force times units of time, which are newtons times seconds. Units of mv are kilograms times meters per second, units of mass times units of velocity. Now, if the change in impulse is if the impulse is going to equal the change in momentum, then these two units had better be the same. Well, we can see that the units are equivalent. Newton times a second. A newton is a kilogram meter per second squared. Multiply that by a second, and one of the seconds in the denominator is canceled by this second, and we have kilogram meters per second, so that we see the units are completely equivalent. An application of the idea is to a collision of two objects. A collision can be regarded as any interaction in which the two objects exert forces on one another. If two objects exert forces on one another, as they do when they come in contact, by Newton's third law, those forces are going to be equal and opposite. In this case, by Newton's third law, as we said, F12, which is the force exerted on mass 1 by mass 2, or on object 1 by object 2, is in one direction, and F21, the force exerted on object 2 by object 1, is in the opposite direction. So we can say that the vector force F21 is equal to the negative of the vector force F12, or vice versa. Okay, so in a time interval delta t, it's going to follow that that F12 times delta t is going to be the negative of F21 times delta t. Just multiplying both sides of this equation by delta t gives that to us mathematically, and in a common sense manner also. If equal and opposite forces are applied for equal times, they're going to have equal and opposite effects. Now, F delta t is the impulse, and that's equal to change in momentum. Now, the impulse imparted to object 1 is going to equal the change in momentum of object 1, which is the change in m1v1. And that's going to be the negative of the change in, or negative of the impulse on object 2, which is a negative of m2v2. So we see that the change in m1v1 is negative of the change in m2v2. Now, if the masses happen to be constant, then the change in v1 is going to be the negative ratio of m2 over m1 times the change in v2. And we obtain this just by factoring the m1 out of the change here, the m2 out of the change here, which we can do if those are constant, and just solving for v1, dividing both sides by m1, we get this. Okay, so this is another form in which we can look at the conservation of momentum, or the idea of impulse momentum. This is actually conservation of momentum because it tells us that the change then in m1 v1 plus m2 v2, which is a change in m1 v1 plus a change in m2 v2, since a change in m2 v2 is the negative of the change in m1 v1, the change in this quantity here has to be 0 because the change in this quantity is equal and opposite to the change in this quantity. And another way of saying that is that m1 v1 plus m2 v2, where v1 and v2 stand for the velocities before collision, is the same as m1 v1 prime plus m2 v2 prime, where v1 prime and v2 prime stand for the velocities after collision. And this is the probably most common form of what we call the law of conservation of momentum for two particles, or two objects.